So here was the state of the affairs at the end of the 19th century. People believed that all matter was made of atoms. They believed that atoms were indestructible, that you could not cut them, you could not break them down into smaller parts. They also knew about electricity. They had just discovered it, and they were very excited about the possibilities of it. They were doing things like building generators, like building incandescent light bulbs. They were doing useful work with it. But they didn't really understand where it came from or how it worked. Now, a lot of that changed when someone, his name was J.J. Thomson, sat down and did a series of very careful experiments with this object, which was an aristocrat's toy at the time. It was a toy because it did something kind of neat. It is basically a glass tube that has got all of the air sucked out of it. It's got a little metal plate here and another little metal plate here. This one has a hole cut through the center, so it's kind of like a donut. You have a wire coming out of each plate. You can hook this wire to anything that's negatively charged, like the terminal of a battery, like a generator, anything, a static charge. And you can hook this one to something that's positively charged. And it does not matter where the charges come from, because what we're about to see has everything to do with what the cathode is made out of and what's happening on the cathode, and really nothing to do with how you put the charges on here. But the charges need to be there. Now, once you turn these charges on, you see something that is kind of interesting. The glass on the end here will start to glow. Now, you can enhance this effect by coating the end of the tube with something like phosphor or zinc sulfide or something. It will glow a lot brighter when you coat it. And they discovered that you could take this dot and you could move it up and down using a magnet or using a charged plate. You could control where the dot was. You could move it anywhere you want, and you even could paint pictures in the phosphor because the glow would persist a little while. And that was the beginning of television. This was kind of a precursor for television, this little toy. The cathode ray tube, it's called. Now, why is it called that? This plate that has the negative charge on it is called the cathode. This plate that has the positive charge on it is called the anode. And if you take a little piece of phosphor and you trace it along the path here, you can see that there's an invisible beam there. It will light up the phosphor if you have a little phosphor tracer that you can put in here to see where the beam is coming from. And it looks like this stuff is boiling off this cathode, and it's accelerating towards the anode, going through that hole, and then it hits the spot on the end. And this thing they called a cathode ray because they could tell pretty clearly by placing phosphor screens along the way what the path was and that it was coming from the cathode. Now, what's this cathode ray made out of? Is it a kind of light? Is it a stream of some kind of particles? And where do the particles come from? They come from the cathode, but are they atoms of the cathode that are boiling off? What are they? J.J. Thomson did a series of very well thought out experiments with this to see what the cathode rays were made out of. And he discovered something that fundamentally changed people's ideas about the structure of the atom and their ideas about how electricity worked. He got a Nobel Prize for this experiment that we're about to describe. Okay, so there are a couple things you can do to see the nature of the cathode rays, and some of these cathode ray experiments are shown in videos that are linked below this one. So after you watch my talk, go and watch those. Here's what the first video shows. They tried to put a paddle wheel in here. So they have like a little wheel with blades on it, rotors. Now when you shine light on a little paddle wheel, it doesn't go anywhere. The light does not have enough momentum to turn the paddle wheel, but this cathode ray does. When you put a paddle wheel in the path of the cathode ray, apparently these particles have some push. And that tells you that this isn't light that we're dealing with here. So our observation is particles can push the paddle wheel. That means that we can just say instead of particles, because that's kind of a conclusion, isn't it? The ray can push the paddle wheel. And that suggests that the ray is made out of particles with mass. They have some mass. They have some oomph in a collision. They're colliding with the paddle wheel and pushing it a little bit. So on this side we have some observations. On this side we have conclusions that we can make. What else can we do? Well, okay, we've established they're particles and they have some kind of mass. Are we really, really sure that this isn't just light? Another thing that they did was they put some kind of a target in here, and they used Maltese cross a lot. You'll see them use this. They put a Maltese cross there, and they looked at what they saw on the end. And what they actually saw was that the Maltese cross would stop the beam, so it can't go through a little metal cross. It was a little aluminum cross. And they saw that they got like a dark spot here where it wouldn't glow, and it would glow around the edges of the Maltese cross. So it would cast a sharp shadow. The cathode ray, the ray casts sharp shadows. Now what exactly does that prove? Well, it means that the ray must be traveling in straight lines to be able to cast the shadow. Now I've shown like one ray here, but really the ray is like, there are a lot of rays and they're all kind of going through the hole like that. So it's not just one little line like that, it's like a bunch of them. And you will see a sharp shadow here. And you would only see it, if I've drawn it a little bit better, you would only see it the size of this hole where the glow was here. So there'd be kind of like the image of the hole on the end there. And that the fact that it casts sharp shadows, it means that these particles move in straight lines. This also suggests that what you have here are particles, not light. Because if you've got light, when it passes around an obstacle or an edge, it can bend around it a little bit. That's called diffraction. Diffraction is really how a camera works. So if you have like a little slit here in your camera, and you have light, which turns out to be waves, we'll see later. Here are some waves approaching the little hole. Light can bend around the edges of the hole and come out like this. So here's the aperture of your camera, and here is your sensor. It will expose the entire sensor, so the light can bend around the edge of the hole. This couldn't do that. It had to go in a straight line. And that was more evidence that this isn't light, and that it was a stream of particles. So that's a conclusion that we can draw by putting a little Maltese cross in there. Now, here's where things get a little more specific, and this is what won J.J. Thomson his Nobel Prize. What kind of particles are in here? Well, one of the things that you can do is put a positively charged plate here and a negatively charged plate here, and see what that does to the beam. So the beam is coming out of this hole, and it goes and it bends this way. And the spot that you'd see would be up here. So it bends towards the positively charged plate. That suggests it's negatively charged. There are negatively charged particles in here. So far we've determined that there are negatively charged particles that have got a mass that are coming through. Now, where are these particles coming from? Well, they're boiling off the cathode here. What if I try to make the cathode out of some kind of different material? It doesn't matter. Whatever material you put in the cathode, and whatever way you put charges on these things, it really does not matter. You always get a beam that acts the same way. You can measure this deflection angle here between these plates, and you'll see that that deflection angle is the same no matter what the cathode material is. Let's put that down as an observation. They don't depend on the material that you make the cathode out of. So they're coming out of the cathode, and then they'll come out of the cathode no matter what it's made out of. Well, a conclusion that you can make here is that these particles are present in all materials. You can say that they might be a universal constituent of matter, that they may be a particle that are found in all atoms, and we're actually breaking apart an atom here, and these particles may be coming from inside atoms. Now, further experiments were necessary to prove that. That's kind of a far leap to say that it's a universal constituent of matter, because you're going to have to examine a lot of different materials to confirm that. But this is an explanation that does account for why you can change the cathode material without changing the cathode ray properties. Okay, now we can nail it by putting a magnet here. So if you take a magnet and you put it here, charged particles will be deflected by a magnet. Now, it depends on where you put the North Pole and the South Pole. But when you put a magnet there, there's a force that acts at right angles to the magnetic field and to the direction that you're traveling, and it will cause the beam to deflect. And if it would have deflected one way, it would have indicated positively charged particles. If it would have deflected the other way, it'll be negatively charged particles. There's a there's a mnemonic that people do with their right hand in physics to see how this works. Your thumb should face the way that the beam is going here, and then your fingers should go the way the magnetic field's going. The way I've drawn the magnet, if it's the north pole in the front here, then the magnetic field's going in the direction of my other finger. So my thumb is going this way, and my fingers are going back into the whiteboard. And if the particles are positive, they're going to bend up out of my palm. And if they're negative, they're going to come down out of the back of my hand. And that's exactly what they do. So this is showing you that you've got negatively charged particles. It's kind of confirming what you saw with the positively charged plate. And we can just say, don't worry about all the detail I just gave you there. Magnetic field bends the ray in a way it does in the same way. Let me say, in the same way it bends negative particles. So your conclusion would be, again, that these are negatively charged particles. Further, it will only bend them if they're moving. So there's some speed on this. Now, this is probably the least clear of all these things, because you're probably wondering about the magnetic field and how that works and all of that. But the fact is that whenever you've got a moving charge, let me write this down. It's a physical fact that we're going to use a little bit later. Any moving charge has a magnetic field of its own. So if you've got a particle that's moving this way, and you've got a magnetic field that it's moving through, it will go ahead and deflect. And when it's deflecting, when it's moving like that, it's because it's creating a little magnetic field around itself that's interacting with your magnet. Now, let me show you some experimental evidence of this fact. Suppose you take a wire. So here's a copper wire, and you've got electric current going through it. Now, put a cardboard card here. So punch your wire through a card. Now sprinkle some iron filings around it. And you'll see all the little iron filings kind of line up around the wire. And what they're doing is they're aligning along the magnetic field lines that you're creating. When you have moving charges in this wire, they create a magnetic field around themselves, which can make the iron filings here line up. And if you put a compass next to the wire, you will see the needle move. The magnet in the compass will try to align with the magnetic field that the moving particles will have. So this is kind of what's going on here. A moving charge has a magnetic field. So anytime you have a moving charge and you send it through a magnetic field, it will bend. And we can conclude then that we have negatively charged particles there. Now, the brilliant thing that Thomson did to put all this together was he did some math. He went back to the cathode ray tube, and he put a magnet there of known strength, and then he added some plates here. He put the charged plates here, and he tried to balance the electric field effect against the magnetic field effect. There are, and you don't have to remember these equations, there are a couple of equations here that he put together. First of all, if you've got a beam and it's being bent around it like you can imagine a circle, and you can actually bend this beam enough so that it does double back on itself and make a circle, you can talk about the radius of the curvature of this. The force that's acting on the beam looks like this. Here's the mass of your little particle. Here's its speed squared, and here's its the radius of curvature here. So you can measure the radius of curvature here experimentally. If you look at the force that's produced by an electric field on this thing, here's the force you're putting on the beam, here's the electric field strength, and here's the charge on the particle. If you look at the force that's produced by a magnetic field, here's the strength of the magnetic field, here's the charge, and here's the speed of the particle. Now you got three relationships for the force that is twisting this stream of particles out of a straight line. And he put these all together. And you don't have to remember those equations or see how algebraically he put them together. But you can measure with this cathode ray tube the charge to mass ratio. That's what Thomson did that earned him the Nobel Prize. He measured the charge to mass ratio for these little negatively charged particles in the beam. And he called them electrons. So he couldn't tell what the charge was, and he couldn't tell what the mass was, because you don't have enough equations for that. But he could tell the charge to mass ratio. Now, when you can measure some kind of specific property quantitatively about something, it kind of suggests that the something really does exist. Now, there's a separate experiment that I'm not going to talk about that they talk about in your book, and it is called the Millikan oil drop experiment. It involved an experiment where you were looking at how little oil droplets that had a little charge on them were spended in an electric field. And you could figure out that the charge on all the oil droplets was some kind of multiple of something. There was always a number that it was a multiple of, and it turned out that that multiple, that number that all the oil drop charges were multiples of, was the charge on an electron. That's really what was important about the Millikan oil drop experiment. I would be happy if you just knew that one fact about it. Okay? The important point is, if Thomson gave you the charge to mass ratio and Millikan gave you the charge, then you could find the mass of an electron. It's about 1,850 something, sixth, I think, the mass of a hydrogen atom, which was very surprising to people because hydrogen atoms were the lightest atoms known. So this is much, much smaller than that. And this suggests that what we found here, this electron, is actually a fundamental constituent of the atom.